Okay, we're ready to pick up our demonstration of using axiomatic semantics. Again, we are using the rules and axioms to generate proofs that a particular Hoare triple is true. Right, and a key thing here is this generation process, that we use the rules and build the proof structure that then is the evidence that the Hoare triple we are interested in is in fact valid. So we've worked through the couple simple examples with using axiom of assignment and the rule of consequence. We can now take another step forward and use the rule of composition. So we'll look at the third one on the slide here, which has two assignment statements. So we'll put this over here in our scratch pad on the side here and realize, all right, we have to do something with this construct. And so we have a few options here. We can use the rule of consequence if we are interested in doing that. Otherwise, we have to use the rule of composition. So let's bring up all the rules again so they're there in front of us. All right, when you're working on these, it's best to have these out in front of you so they're there to observe. All right, so again, we are treating this as sort of a two-step process, one discovering the proof and then writing it up in a nice way. So here we can look at this and say, well, obviously we need to use the rule of composition at some point. So let's think about trying that. So we can take the Hoare triple at the bottom and turn it into two Hoare triples above using the rule of sequential composition. Right? So our question now is, what is Q? And is Q going to be something that will give us the precondition of b equals 5 on the first assignment? So if we apply the axiom of assignment on the second condition, right, we will generate a Q that's the weakest precondition of this assignment. I'll abbreviate the rule over here. And so if we do this, right, the question then is, what does Q become? And so again, this rule tells us that we replace the variable being assigned to with the expression. So we get 2 times b equals 20. Right? And so that's our application of the axiom of assignment. What about this piece over here? Right? So let's grab this and move it up a bit. Right, and so unfortunately my editing window here is a little bit narrow, so we're going to stack these things a little bit and do things that way. Right? On paper you will also have to be a little inventive sometimes. Alright, so our post condition here is presumably 2 times b equals 20. Right? We need the same expressions here, that the post condition after the first assignment is the same as the precondition of the second assignment. So that's what we need to get. And again, we can consider what our axiom of assignment will do. Right? So we can put this up here and say, well, what would the axiom of assignment generate for us? Right? All right, so what goes here? Well, we take that assignment and we replace b in the post condition with the expression. So we get 2 times b plus 5. Right? Note we have to wrap this in parentheses. So this is a more of a structural replacement as opposed to some textual replacement where we just paste the characters in. Right? So the structure here must be maintained. And so we add the parentheses to make that clear. All right, and so this is what we get with the axiom of assignment for our first assignment with the post condition that we generated from the second application. Right? But that's not quite what we need at this point. So what we really need to do now is make an application of the rule of consequence. And so it's going to be this piece, as well as something that strengthens the precondition. Right? In this case, we don't really strengthen it at all, so much as we see that the r and the r prime that we see in the rule are going to be the same. So one implies the other, but we only care about the implication in one direction. All right, so in this case, we're trying to get an r, which is b equals 5. Right? And so if b is equal to 5, that certainly implies that 2 times b plus 5 is equal to 20. Right, so we now have our two components. They're stacked here a little bit, but we certainly see that we have this axiom of assignment application here. So this corresponds to this Hoare triple in the rule of consequence, and then the strengthening of the precondition is this other piece here. Right, so we've left off the bit about weakening the postcondition, and so the rule of composition as it's written here is really two rules. Right, one where we can strengthen the precondition and another where we can weaken the postcondition, or we could do both at the same step. Right, but we don't need to do both. And so at this point, if we look at this, we have the right proof. We have our axiom of assignments as sort of the leaf nodes of our proof tree. We also have this statement here as a leaf node of the proof tree, and we then construct the tree accordingly. So this proof is one in which we were very careful about using the rules of axiomatic semantics, but we weren't so careful about the rules of mathematical logic or the rules of integer arithmetic here. Right? We kind of waved our hands and says, well, it's pretty obvious to us if b equals 5, then 2 times b plus 5 is equal to 20. Right? So here we are now stepping out of the logical framework for axiomatic semantics and making a claim in another logical framework of integer arithmetic. And so in that case, for these integer arithmetic expressions, we don't formally prove those. We rely on our intuition and experience to be sure that those are correct. All right, so that's our second one. We might move on to the next one, and that one is a proof about this GCD program. So to keep all these videos short and manageable, we'll pause here and start another one for the proof of the greatest common divisor program.